Hello, everyone. My name is Daniel Durnford. I'm a PhD student at the University of Alberta, and today I'm going to be talking about new results from the NEWS-G light-dark matter experiment. The lack of discovery of canonical WIMPs in recent years on sort of the 10 to 1,000 GeV mass range has motivated other experiments to look for lower mass WIMP-like dark matter candidates. These could be things proposed by theories like asymmetric dark matter and would typically be on the order of about 1 GeV or less. And NEWS-G is one of the relatively small number of experiments that's sort of pushing into this new region of parameter space on the exclusion plot. Specifically, we use spherical proportional counters to look for low mass dark matter. So these are metallic vessels that are filled with a noble gas mixture, typically containing things like neon or helium, usually with some hydrocarbon like methane as well, so we can get some sensitivity from hydrogen. There is a single high voltage electrode in the center of the detector that serves as a sensor. Having the low A target gas definitely increases our sensitivity to low mass dark matter, as well as having a large signal gain from the Townsend avalanche process that is characteristic of proportional counters. This lets us have a very low energy threshold, sort of on the order of 10 electron volts, which is critical for these searches. Specifically, how the detector works is when you have an ionizing interaction in the gas, some stochastic number of primary electron ion pairs is produced. The statistics of that are dictated by the so-called W value, which is an intrinsic property of different gases, or electronic versus nuclear recoils, where it's scaled by the quenching factor. From there, the primary electrons that are created sort of drift and diffuse through the gas towards the high voltage anode, typically over the course of hundreds of microseconds or so. When they reach within about a millimeter of the anode, the primary electrons are sufficiently accelerated to induce further ionization, creating an exponential cascade called a Townsend avalanche. And it's this process that gives us such a large signal amplification. At that point, it's actually all of the secondary ions drifting away from the sensor that induces a current that we can actually measure through a charge-sensitive preamplifier and then digitize. This is an example of what a pulse from a single primary electron looks like. So you can see that we're capable of having a very good signal-to-noise ratio for even single electron events. And with this technology so far, NEWS-G has successfully operated a 60-centimeter diameter sphere filled with the neon gas mixture at the Laboratoire Souterrain de Modane in France. It's an underground lab just on the border between Italy and France, underneath the mountains. It's very, very nice. With that experiment, we were able to set, at the time, a world-leading exclusion limit on dark matter particle with a mass of 0.5 GeV. But we've since moved on to the next bigger and better phase of our experiments, a new 140 centimeter diameter sphere. It is made of very radiopure carbon and surrounded by a very radiopure shielding setup that includes archaeological lead in the center, a further 20 centimeters of low activity lead, and then 40 centimeters of polyethylene shielding that was actually manufactured at the University of Alberta. In addition to all of the sort of hardware upgrades to the detector itself, we've also put a lot of effort into our gas handling and gas quality, including filters to remove electronegative contaminants from the gas like water and oxygen, as well as the removal of radon from the gas as well, which is also a product of the University of Alberta. We've also put a lot of effort into improving our sensor technology. In particular, sort of a key element to being able to scale up to such a large detector is having a sensor that gives you a strong electric field near the anode, so you can have that signal amplification, but also a strong electric field all the way to the outside of this large sphere so that you can actually collect electrons that are created. And the solution to that was to actually make a multi-anode sensor. We nickname it the Akinos, which is Greek for sea urchin. And you can see this particular design here at the bottom has 11 individual anodes that sort of allow us to scale up to this size. We've also put a lot of effort into mitigating our main background source in our detectors, which actually turns out to be from lead-210 that is incorporated into the copper of the vessel itself. But it's not actually alpha decay from the lead-210. It is Bremsstrahlung X-rays produced by beta decay of lead-210 and bismuth-210. These Bremsstrahlung X-rays, if they escape the copper, can easily travel throughout the entire detector volume, giving a uniformly distributed low energy background, which is a big problem for us. In collaboration with XMass, we were able to use alpha counting to measure the level of lead-210 contamination in our copper to be about 30 millibecquerel per kilogram. To mitigate the impact of this contamination, we worked with PNNL to electroplate 0.5 millimeter of pure copper on the inside of the entire vessel. You can kind of see what that electroplating setup looks like here. Even just that small amount of copper actually greatly reduces this background. Below 1 kV, it reduces the Bremsstrahlung X-ray rate by about 70%. So this is definitely a huge step forward for this particular detector. But we are already looking at future improvements to further deal with this problem, including an entirely electroformed sphere. But for details about that, please see the talk by my colleague Costas, which is also in this parallel session as well. So with this new detector, we were first able to take some commissioning data, again at the LSM in France. We had the unique opportunity while there to actually take data with pure methane gas. This is something we usually won't be able to do because of safety concerns. But the nice thing about the pure methane is the larger fraction of hydrogen and greater transparencies to high energy gammas actually gives us sort of a better signal to background ratio per unit mass than the typical neon gas mixture that we will use in the future. And one of the cool things actually we found out right away when we operated this detector is that the combination of very large diameter as well as the very slow drifting methane gas that we use, we were actually able to resolve individual primary electrons in time as they arrive at the sensor. So each one of these individual spikes you can see in these sort of treated pulses is actually from an individual primary electron. So this lets us do lots of cool analysis things like peak counting. This helps us both select physical events or reject non-physical events sort of outside of our energy region of interest. So there's lots of fun analysis that can be done with this. Just sort of in contrast to the typical situation for us, where for smaller detectors or faster drifting gases, typically all of the primary electrons arrive at once. So in these example events from argon-37, there are probably about 100 primary electrons in each of them, but you just see sort of one pulse. Another really cool side effect of this new sensor technology we've developed is crosstalk between the two readout channels that we have. So for the Akinos sensor, even though there are 11 separate anodes, we actually currently read them out just in 2 channels, the 6 southern anodes and then the 5 northern anodes. And this little animation just shows you what sort of the electric field structure looks like around that sensor. And we actually see really clear crosstalk between those 2 channels. So whenever you have a positive pulse on one, you see a smaller mirrored pulse on the other channel. So you can see here some positive south pulses and then the corresponding negative north ones. The cool thing though is that this seems to only happen for physical events where you actually have amplification happening in the gas around the sensor, not for non-physical electronic noise events. That can happen sometimes if you have a little discharge within inside sort of the central element of the sensor or something like that. So this actually gives us a really powerful tool to discriminate against non-physical backgrounds as well. So another sort of cool perk of this new setup. So with this initial commissioning campaign, we were able to take 12 days of data with pure methane gas. The analysis of those results is still ongoing. Some of the key calibration results that you can expect to see are first from our UV laser calibration. This is what the data from that looks like on the left. With this, we're actually able to detect all single or few primary electron events, which lets us directly calibrate our single electron response. So it's a very powerful calibration tool. Additionally, we also use argon-37 as a calibration source, which is very useful. It's a gaseous calibration source, so it lets us measure the detector response for the entire volume. It also gives us decays at 2 different energies, so we can confirm the energy linearity of our detector. Between the two, we can come up with a sort of overall model for our detector's energy response, all the way down to single ionizations. So results from this can be expected very soon, which will be exciting since it'll be the first dark matter exclusion limit set with hydrogen target atoms. So definitely keep your eye open for those results. But we've now actually relocated this detector to Snow Lab in Sudbury, Ontario, Canada. This is another underground lab in a nickel mine, which is actually sort of the intended home for this detector. You can see a picture of the vessel being carted through the mine tunnel and then lowered into the cube hull. For those of you who are familiar with SNOLAB, this is actually right beside the deep 3600 dark matter detector on the right. And despite some initial sort of delays because of the pandemic, we've been able to carry on with construction in more recent months. You can see this little time lapse here, what that looks like. There's the bottom of our lead shield on top of the polyethylene shielding, and then the sphere being lowered in right about there. There it is. So despite the initial delays from the pandemic, we've been able to actually complete the installation of the detector, including the shielding and all the electronics and gas handling setup. And then actually just in recent weeks, we finally actually saw first light from this detector in its new home. And there's a little news article you can read there if you want to know more about that. So we're very excited to begin this next phase of our experiments. Initially, the plan at SNOLAB is to use a neon and methane gas mixture. And with some assumptions about our background and energy threshold we can achieve, we expect to be able to set world-leading exclusion limits all the way down to a mass of 0.1 GeV, so much, much lower than previous experiments. So we're very excited to see the new physics results that come out of this, so definitely keep your eyes open. That is all from me. Thank you very much for your attention, and hopefully talk to you all soon in the interactive session.